With this temperature model we've been studying, is it possible to figure out the temperature of the room by taking several measurements of the way an object changes temperature? And now when you look at the function, temperature at time t of our object is a constant times e to the kt plus the temperature of the room, which is constant. So actually there are three constants here, c, k, and t. Now in order to solve for three unknown pieces of information, we'll need three pieces of information. And so before, the last problem we did, this was given to us, so we needed two temperature measurements in order to fill out this function. But now if we want to know the temperature of the room, I need to know three pieces of information, three measurements. All right, so suppose that the object is at 20 degrees at the beginning initially. So we bring it out, it's cold, it's 20 degrees, and it starts to warm up. So this is also a little different from the last problem. Instead of cooling down, this object is warming up. So suppose that after 10 minutes, the object is up to 42 degrees. And then one more measurement after 24 minutes, the object is now up to 54 degrees. So, what is the temperature of the room? Let's see if we can do this. Now, I did work this out on the side, and it's pretty messy, but let's go full steam ahead here. So, using our initial condition, t at 0 would be c times e to the 0, so that's just c, plus tr equals to 20. So that allows us to solve for our constant c. C would be 20 minus tr. So now my function is t of t is 20 minus tr e to the kt plus tr. So that's the first piece of information used. Now let's go on to the second one. After 10 minutes, we're at 42 degrees, so I'm going to plug 10 in for t here. I have 20 minus tr e to the 10k plus tr is equal to 42 degrees. And now let's solve for k. Now you might wonder, well, why don't we solve for the temperature of the room? Well, because we still have another constant k. And I think it's going to be easier to solve for k than it is for tr here, perhaps. Well, let's just do it anyway. So I'm going to subtract tr from both sides and then divide by 20 minus tr. So I have 10, e to the 10k. E to the 10k is equal to 42 minus tr divided by this parentheses, 20 minus tr. And now k, to get it, we'll take the log of both sides and divide by 10. So k is natural log parentheses 42 minus tr over 20 minus tr, all divided by 10. Well, that takes care of that piece of information. So it's getting pretty messy here. Let me do some erasing, and we'll write out the function, this function, using this k value. So I took this function and I replace k with this rather ugly thing here, and that's k times t plus tr. So here's my temperature function, and I have one more piece of the puzzle to plug in, and this should hopefully allow us to figure out what the temperature of the room is. So, but we can do something to help ourselves here. We should take advantage of this e to the natural log. So if I rewrite this, parentheses 20 minus tr, and factor out the t over 10, I have e natural log 42 minus tr over 20 minus tr, and times t over 10, well, that means this is to the t over 10 power plus tr. And so that allows us to cancel off part of this mess And we end up with, well, let me erase again. I'll rewrite this. So I cancel the e in the natural log here, and I have this parentheses raised to t over 10 times the 20 minus tr plus tr. That's our function. Now, we haven't plugged in the last initial condition, which is 24 minutes. It's now warmed up to 54 degrees. So t at 24 minutes would be 20 minus tr parentheses 42 minus tr over 20 minus tr raised to the, now 24 over 10 is 2.4, so I'm just going to write 2.4 here for convenience, plus tr is equal to, what was it, 54 degrees. Okay, now that is that's quite a mess, and we want to solve for tr at this point. It's not going to be easy. We could use Newton's method to approximate tr here, and that would be by subtracting 54 set equal to 0, and then approximate it by using Newton's method. Or we could use our modern technology, which I've chosen to do, to approximate it. So what I did was I subtracted 54 from both sides. So I ended up with this function, 20 minus, and here's how I entered it in my calculator. I let x be the same as tr. So I have 20 minus x, parentheses, 42 minus x over 20 minus x raised to the 2.4 power plus x minus 54 equals to 0. So I took this and plugged it into my calculator as if it were a function, y equal to this whole mess in terms of x on my calculator. And then I want to know where is it equal to 0, so plugged it in and I graphed it and I zoomed in and I have an approximate answer. The x is about 59.75. So the temperature of the room, the room temperature is about 59.75 degrees. So that's pretty close. And I was able to do that in a matter of maybe 2 minutes. Plug all that in and fiddle with my graph in order to zoom in and figure out where it crosses the x-axis. Where it crosses the x-axis is the root of this equation, where y equals to 0. So there we go. Not terribly easy to solve. We have to do some approximating techniques there, but it can be done. So I thought that was a pretty interesting problem.